So it's a pleasure to have Hugo Duminil-Copin from IHS in the University of Geneva to continue our session. I would like to point to a mistake from the organization, and the title was the title of the proceedings, right? So, but he took the challenge and he's going to talk to us about 6 years of percolation. So please.
Yeah, well, thank you very much, Hugo. So, I got a little bit stuck with this title, which, well, I don't promise I will be able to present everything about percolation in 45 minutes. Especially these things are always difficult because I guess 90% of you never heard about percolation, and 10% heard way too much about it. So, I mean, I don't know how to, now that I see all the faces, maybe 90% was optimistic. But I did do the slide in such a way that 90% of them are of no interest if you already heard about percolation. They are really attended to people who never heard about it. But I promise for the people who heard about percolation, you can sleep for this first part, but wake up at the end because there will be really a new theorem, which I hope I will manage to motivate through the 91st percent. Okay, anyway, so let me start by trying to tell you why, I mean, where percolation comes from and what is percolation. So percolation was introduced actually to try to model a very honest applied problem. It was introduced by two English people, Broadbent and Hammersley. Broadbent was not a mathematician, he was an engineer. And Hammersley was really a hard believer in applied mathematics. So it really started from applied mathematics, and the idea was to try to model just a porous medium into a bucket of water. So how the water goes through this medium. And the idea of Broadbent and Hammersley was to say, okay, I don't know how it is in my stone, so I'm going to model it randomly by saying in my stone there are atoms, and these atoms are connected by bonds, which are either dammed or undammed. If it's undammed, then the water can flow between these atoms, otherwise it cannot. So that's the original model that they introduced. And the point is that, of course, it does model water, I mean, porous medium, but more than that, it actually models many other mathematical, physical systems, including, for instance, disease, infection, or more interesting, electrons migrating over an atomic lattice. So there are many applications in physics of this model, actually. Okay, so mathematically, what is the model? The model of percolation is just a model of a random subgraph of a given graph. You give yourself a graph with vertex set V and edge set E, and you want to pick at random a subgraph of this graph. So we will pick at random very special subgraphs in the sense that they will have the same set of vertices. The vertices never move, you keep all the vertices, and just you pick a subset of the edges, okay? So the subset of, I mean, the edges of your graph is a subset of the edges of your original graph. And because I don't want to be referring always to this random graph omega, I will say that an edge of my original graph is open, like open to the passage of water, if it's in omega, and it's closed otherwise. So I will always speak about open and closed edges. Good. Of course, there are like many ways of creating randomness. But the simplest one, maybe, and that's the one that was introduced by Hammersley and Broadbent, was to say, well, in order to decide whether an edge is open or not, I toss a coin. If it's tail, I say it's open. If it's the opposite, I say it's closed. And let's say it's a biased coin. So let's say my edge is going to be open with probability P and closed with probability 1 minus P. And my coin, I retoss it for every edge. So the state of edges is completely independent. Every edge has a different, has independent states. Okay, very simple model. Here, these are beautiful pictures, so obviously they are not due to me. Okay, this is Raphael Cerf, and this is applying also to the next pictures. All the nice ones are not due to me. You can complain about the bad ones later if you want. But, so this is p equals 0.49. So you favor a little bit more the closed edges than the open one. And here what Raphael Cerf did is that he colored the connected components of my graph in different colors. And here you see that the connected components are all fairly small. Here it's for p equals 0.5, so you see that the connected components become macroscopic, like you have big connected components, but it seems that you still have many big ones. And this is for p equals 0.51, where one connected component is huge, and the other connected components are quite small. These are simulation, of course, realization of this random subgraph. Okay. Just before, I will basically just speak about Bernoulli percolation, but I just want to make a parenthesis because you could argue that this seems to be a very special way of picking randomness, and you are right. I mean, there are many other ways of picking, and I just want to make a list of a few examples which are also very important percolation model, and maybe if I would have been able to choose another title, I would have told you about my research, which is basically studying these other models. So, but anyway, the first one, for instance, is called the Fortuyn-Castellan percolation, and it's the following. So if you want to write the probability measure associated to Bernoulli percolation, well, it's very simple on a finite graph. It's just a product measure, so it's probability of a configuration is proportional, is equal to p to the number of open edges, 1 minus p to the number of closed edges. But imagine now that I add a new parameter q, and that I put an energy parameter, which is q to the number of connected components. If I do that, my model is not independent anymore. Like the state of edges depends through the count on the number of connected components. So if you are a little bit careful, you will realize that this is a positive measure, but it's not a probability measure. Its mass is not 1. So just you renormalize it in order to get a probability measure, and you have the Fortuyn-Castellan percolation. You could ask, why do you why do you create these dependencies between edges in this way? In fact, this model is related to a large class of spin models called the Potts models, which are fundamental model of ferromagnetism. They are related to this percolation model, so it's very important to understand this percolation model. You have other ways of creating randomness, and one thing that you could argue is that maybe you don't want to be working on a lattice. I mean, why do you, my stone is not made of crystal with atoms that are very evenly spaced. So you could think, for instance, that's not what I planned. At least I didn't press on the wrong button. Apparently this one does something, I don't know what. Maybe it turns this off, maybe it does something worse. We will see at the end. But okay, one thing you could do is just put your atoms randomly themselves. And one way of doing it is, for instance, to put them via a Poisson point process. So you are going to put your atom in a random way. And then, for instance, you can decide to draw the Voronoi cells of the atoms, meaning the points that are, like the cell of an atom is just the points that are closer to this atom than any other atom, and then say that a cell is open or closed with probability p or 1 minus p. You end up with a model, which is called Voronoi percolation, which is a very interesting model on its own. So you can modify like that your thing. More recently, there was something maybe even more interesting happening, is that people started to study percolation models that are constructed from random height function. So a function which is valued into real numbers. And this random height function can be really defined in different ways. It could be, for instance, a random homogeneous polynomial. It could be a random sum of eigenvalues of Laplacian. It could be also the Gaussian free field, which is a very famous object in statistical physics. And just to tell you quickly, because it's going to come back at the very end of the talk, the Gaussian free field is just the measure which, density is proportional to exponential of minus 1/2 of the sum of the difference between neighboring vertices squared. This is called the Dirichlet energy sometimes. So it is maybe the most canonical example of a Gaussian field, that a Gaussian process that you can imagine in statistical physics. So you take this, and you look, you say a vertex is open, an atom is open, if the value of the field is larger than a certain parameter, and it's closed otherwise. This gives you, again, a model of percolation. There are, very intense research in this area, and in this one, dozens of papers a year. Okay, that was just a parenthesis. I'm not going to talk about these guys anymore. I go back to, this is very intimidating, this countdown. Combined with that button, it's, anyway. Let me go back to percolation, Bernoulli percolation, and let me just give you like the simplest thing you can prove on Bernoulli percolation. We are going to do a proof together almost. And it's a question of understanding whether there is an infinite connected component in my graph or not, depending on the value p. So let me define theta of p to be the probability that 0 is in an infinite connected component of omega. And just observe that, for instance, it's quite simple to prove that if p is sufficiently small, theta of p is 0. And one sufficiently small, one way of meaning sufficiently small is to say, not that, is to say, define what we call the connective constant of the lattice. It's basically the rate of growth of the number of safe-avoiding paths starting from the origin of length n. So you take safe-avoiding paths of length n starting from the origin. You have a finite number of those. Let's call it Cn. And if you are bored, you can try to prove that Cn to the power 1 over n converges to a certain constant. It's called mu of your graph. So in this case of ZD, it's mu of ZD. And the observation is that if p times mu of ZD is smaller than 1 strictly, then there is no infinite connected component. 0 is connected to infinity with probability 0. And it's quite simple to see, because if you think about it, if 0 is connected to infinity, it's connected to distance n at least. So there must be a safe-avoiding path starting from the origin of length n, which is only made of open edges. It's absolutely mandatory for the event to occur. But for each one of these paths, the probability to be made only of open edges is p to the number of edges, so it's p to the n. So p to the n times mu to the power n plus little o of n, which is the number of possible paths. If p times mu is smaller than 1, this thing is tending to 0, and it's actually tending to 0 exponentially fast. Very simple, nothing very deep there, but it does prove that for small values of p, you have no infinite connected component. Another thing, which is actually not true, and this is the content basically of the first paper on percolation. Another thing which is easy to see is that if you are on ZD and D is larger or equal to 2, when P is close to 1, in fact, you have an infinite connected component with positive probability, in fact, with probability 1. And the way you prove that is by observing that first, well, it's sufficient to treat the case D equal 2 because, ZD is bigger than Z2. So if you have already a infinite connected component on Z2, you will have one on ZD. And then you want to say that, well, for us, that's, again, not what I want to do. You want just to say that in order not to be connected to infinity, there must be a set of edges blocking me from having this path to infinity. And if you take a minimal such set of cardinality n, so this minimal set of cardinality n, for all the edges in this set to be closed, well, that costs me 1 minus p to the n. But now, the number of possible blocking surfaces, when you are on Z2, these blocking surfaces, by duality, they correspond to circuits in the dual graph. So they correspond to safe-avoiding circuits, and this you can count again and basically prove that the number of such objects is also growing like mu to the n plus little o of n. So together with the 1 minus p, it tells you that if this is, I will manage once to do it during the talk correctly, but if this thing is smaller than 1, then in fact you have positive probability of being connected to infinity because you have positive probability of not seeing such a closing surface. I will come back to this and make a drawing in a minute. So this is really like the most elementary things you can do on percolation. I don't think that you are amazed by, if you think that we are only doing that, maybe you will not have a very high opinion of our field, but, well, we are basically doing only that, so anyway, but yeah, in fact, we are not only doing that, because this is only working if you think about it for values of p which are very small or very close to 1. But what we are really interested in is what is happening in between, for values of p which are not so close to 0 or 1. And the first thing that you can observe is that there is a parameter, pc, that depends on your lattice, below which theta of p will be equal to 0, and above which theta of p will be strictly positive. And this is absolutely clear intuitively, because it's just that theta of p is non-decreasing. If theta of p is non-decreasing, define pc to be the infimum of the p for which it's strictly positive, and you are fine. Okay, why do you think it's strictly increasing? Well, you think it's, non-decreasing. Well, because you think that the larger the p, the bigger my graph omega. But if you think about it, it's not something that is so obvious to turn into a rigorous proof. Because if I ask the two gentlemen on the front row to give, like, say, one percolation of parameter p and one percolation of parameter p prime, like, they give me two realizations of that, but they don't speak to each other, they do it independently, then in fact, even if p prime is larger than p, there is positive probability that an edge here will be open, will be closed, and an edge here will be open, right? I mean, whatever the value of p and p prime, you will have probability 1 minus p prime times p, that the edge in the big graph is closed, and the edge is open in the small one. So you cannot do it completely. I completely confused myself, but I think you got what I wanted to say. Anyway, so the point is that you need to be a little bit cleverer, and I just want to make this proof because for people who never did probability, it's a quite interesting proof. It's the notion of, it relies on the notion of coupling, in the sense that if you have two random variables, one which is a Bernoulli percolation of parameter p and one which is a Bernoulli percolation of parameter p prime, you have many ways of making them live on the same probability space. And actually, it's extremely important to choose well the way you make them live on the same probability space. If you do it independently, you have no comparison between omega and omega prime. But if we would manage to construct a probability space in such a way that omega is indeed smaller than omega prime almost surely, then we will be done. And in order to do that, there is a very simple way. There is a very simple way to do is that instead of picking, like tossing your coins for every edge, you just say for every edge of my lattice, I actually attribute a uniform random variable between 0 and 1. This is my randomness. It's a bigger randomness, if you want. It's a real number between 0 and 1. But then, what you do is that you decide that the edge is open in omega if this uniform random variable is smaller or equal to p. And you say it's open in omega prime if the same uniform random variable is smaller than p prime. It's completely straightforward to check that each one of the two guys are going to be percolation of parameter p and percolation of parameter p prime. Just the probability here that the uniform random variable is smaller than p is p, so it's fine. But here, the construction is such that if the edge is open here, it's automatically open here. It's a very simple observation, but it's a very fundamental one in some sense. If you understood that, you understood part of probability in some sense. And once you have this coupling, this probability measure, then it's simple to see that theta of p is smaller than theta of p prime for p smaller than p prime, and you get the definition of PC. That, I mean, I wanted to give this proof because I think it's an interesting go-home message, even though it's obviously very simple. Okay, so now let's really start the history of non-trivial theorems on Bernoulli percolation. And the first one is called the Rousseau-Seymour-Welch theory, which I'm not sure the author at the time realized how much of influential it would be in the last, the next 40 years. So the idea, it starts from a very simple question. Take the square lattice, fix p equal 1/2, and ask yourself, what is the probability to cross, to have an open crossing from left to right in a square box? let's not take a square box, let's take a box which is n by n plus 1, and you are going to understand why. But what is this probability? Well, if you think about it, I mean, if you are looking for a number between 0 and 1, which is not 0 and not 1, I mean, the natural thing you are going to come up with is 1/2. I mean, let's be physicists a little bit. And indeed, this thing is probability 1/2 of happening. And the argument is very cute. You just say, if there is no crossing, so I want to compute the probability of the complementary events, if there is no crossing, the union of the connected components of the right side, well, if you think about it, its left boundary is made of closed edges that I didn't draw here, but in the dual lattice, these closed edges, they correspond to a path in red here, going from top to bottom in the dual lattice. But now, if I forget the original bold open edges, and I only think about this dotted one, notice that an edge, the dotted edge is present exactly with probability 1 minus p, because it's present if the original edge is not present. So the distribution of these dotted edges, it's also a percolation on the dual lattice at parameter 1 minus p, which is also equal to 1/2. But now if you rotate like that, you realize that for the same process, you get the same event as what I was trying to get. The probability of A plus 1 minus, I mean, the probability of A plus the probability of A complement is equal to 1, but both probabilities are equal, so I get probability 1/2. Very simple question, very simple answer. So now, next question, just do it with a more general topological quadrangle. You take, a Jordan curve. You take a simply connected domain. I don't want to blow it to make it bigger and bigger. So what I'm going to do is I'm going to make the lattice finer and finer, and just look at the probability that there is a path of open edges from this to this. If it's a square, it's 1/2. If it's not a square, you can wonder what it is. And the theory of Rousseau-Semmelweis is telling you that whatever the topological rectangle, there is actually constant, such that it remains bounded away between the first constant and the second one. It doesn't tend to 1, doesn't tend to 0. It remains non-degenerate. And this is actually fundamental. This is really a key tool in the study of percolation. It seems like a small step to generalize this type of ideas, but it's actually a nice theorem. It has many, many applications. The first one that come to mind, I will not present it, but the first one is that, in fact, this implies that there is no infinite connected component, almost surely at p equal 1/2. So translated into the PC, it means that the PC is larger or equal to 1/2. One inequality on PC. Just for the story, and if you want a good problem, this thing, in fact, should converge for any domain, and it should converge to a quantity which is called the Cardy-Smirnov formula. And the interesting feature about this quantity is that it's conformally invariant, meaning that if I take two topological rectangles that can be mapped on each other by a conformal map preserving the 4 points on the boundary, I should just converge to the same limit. It's a very strong symmetry of my model, and it's a very fundamental one. We don't know that for this model. We know that for a slightly different model. That's what Smirnov proved. But for this model, it's still an open problem. OK. Next theorem, so this was 78, and 2 years later, there was maybe the main result on percolation theory of the decade that came. It's a theorem by Harry Keston that the critical point, not only it is larger or equal to 1/2, it's equal to 1/2, in fact. And just to mention how how you relate that to the previous theorem, let me mention that the idea of the proof, very briefly, is to basically prove that the crossing probability of my square actually undergoes a Sharpe's threshold. So goes very quickly from a value which is very close to 0 to a value which is very close to 1. And the way it's proved is something that will change the face of the theory for the 30 years that followed, that it's proved by deriving a differential inequality on the probability of crossing. So what Kesten proved is that the derivative of my, the probability of my event is larger than pi n 1 minus pi n times a very large constant, a constant that depends on the size of my graph. Notice that this quantity here is quite natural because this derivative cannot be big if the probability is close to 0 or 1, so this is a natural thing to do, but the important thing is that when this is not close to 0, when we are in this area, the derivative is very large, so it means that it goes very quickly from 0 to 1. This sharp threshold is something which is extremely trendy. I mean, it's very important these days in probability. There are many different theorems. I could have spoken about that for hours, but probably you don't want me to do that. I just mentioned that, for instance, if you change a little bit the differential inequality you want, you can get another theorem which was a milestone of probability. I just mentioned it, I won't be using it, but it's a theorem which is saying that below PC, you know that theta of P is 0. So the probability of being connected to distance n, just by measurability, goes to 0 when n tends to infinity. But in fact, it goes very rapidly to 0. And this is the theorem by Menshikov, Eisenman, Barsky, and with Vincent Tassion, we gave a very nice, I mean, what I think is a very nice two-page proof of it, which is that you have exponential decay of the speed. And this is a fundamental theorem because it allows you to understand very well this P smaller than PC regime. So think of all of this as basically the go message is that P smaller than PC is very simple, and on Z2, I mean very simple, sorry. P smaller than PC is very well understood, and on Z2, PC is 1/2. We can compute it. Okay, so what happened now when we change and we think, okay, we like Z2, it's nice, it's planar, but let's work on ZD. What do we know in this case? Well, first thing we know, and it's trivial from what I described before, is that PC is smaller than 1/2 because clearly it's smaller than the PC on Z2. And second thing is that it's larger than 1 over the connective constant of ZD, so in particular it's larger than 1 over 2D. That's one trivial bound. But if you think about it, and if you try to do numerics, like Monte Carlo simulation and things like that, PC doesn't seem to have any type of nice value for D not equal to 2 or to 1. I mean, PC of Z is obviously 1, and you can try to prove it yourself. So above dimension 2, no good value for PC. Okay, it doesn't stop everybody. So Hara and Slade in the 90s use what we call less expansion techniques, whatever, to prove that the PC, you can have at least an asymptotic when D goes to infinity. You have this nice asymptotic, so you can get things on PC. But more importantly, this less expansion technique allowed to do something which, the first time you see it, is quite impressive in some sense, is that you cannot compute PC, yet you can prove that at this PC, theta of PC is 0. So what they proved, and it was improved later on, is that for any dimension larger or equal to 11, theta of PC, so at PC, there is no infinite cluster almost surely. And this I didn't tell you when I defined PC. I didn't tell you whether that would happen or not. I told you for P strictly smaller than PC and for P strictly larger. But at PC, a priori, you could have either an infinite cluster almost surely or no infinite cluster almost surely. What they say is that in dimension larger or equal to 11, it's always 0, the probability. Hara and Slade, in fact, proved it for very large dimension, and there were refinements that led to this D equal 11, which was obtained in 2015. So you can wonder, okay, maybe you can improve and go down to dimension 3, but in fact, using these techniques, you cannot hope to do better than dimension 6. And probably it will take some time before we reach dimension 6. So it leads to a natural conjecture, and that's probably the biggest conjecture in the field, is to prove that, in fact, you always have theta PC equals 0. Remember, we cannot compute PC. It's defined implicitly, but try to prove that theta PC equals 0. And I like this problem because it illustrates really one appealing aspect of the theory, is that, as Kesten put it, when he came from a honest applied problem, which, I mean, at least in my case, I don't care at all about, But it leads to very beautiful problems, I mean mathematical problems, because these are problems that you can state. I just presented one to you in less than 20 minutes. I could even have done it faster. And well, the solution is non-trivial. You really need to work probably to get it. So it's a very good source of open problems, which people in discrete math, I mean, I hope, I mean, that's what we like. You know, you get a hand-on problem, something you can state easily, and which leads to rich mathematics. So I think probably, I mean, percolation is a good example of this type of things. Okay, but I mean, why stopping on ZD? What happened when you take percolation on a bigger graph? And this idea led in '96 to a beautiful paper. I mean, the best type of papers who contain more questions than answers. So a paper by Benjamini and Schramm, who said, okay, what are the relevant questions when you define your percolation on bigger graphs? And the first setting that comes to mind is to pick a group, G, finitely generated. So let's take a set of generators, S, symmetric, and define the Cayley graph of this group. So just it's a graph that you construct by the vertices are just the elements of your groups, and bounds are connecting two elements of your group that you can obtain from each other using just an element of your generator set. So you get a graph, question, what is PC, or more precisely, I guess, if we cannot do it on Z3, Z4, and so on, can we, for instance, prove that PC is strictly positive? That is clear. PC is larger than 1 over the degree, exactly for the same reason as before. But, for instance, is PC equal to 1? And if you know a little bit about Cayley graph, in some sense, like most of Cayley graphs are much bigger than ZD, but when you think of the argument that we use for Z2, this was very planar. It doesn't apply in a higher dimension. You could try to think of the geometry of these blocking surfaces in higher dimension. Actually, you can even count them and so on. So on ZD, it would work. But counting blocking surfaces on general Cayley graphs, this is a nightmare. It's extremely difficult. So the approach that is, and that's why I wanted to present it to you, because this approach, when you try to do it on general Cayley graph, just breaks down. So it led to, there were many questions and many conjectures in this paper, but the first one was the simplest of the question, which was try to prove that PC is smaller than 1 as soon as you are not linear growth. Again, if you take Z, it's a very simple exercise to prove that PC is equal to 1, but in fact, you can prove that any graph which is quasi-isometric to Z will have the same property. PC is equal to 1, because you have finite cut set, basically. So you can really... So it's actually an if and only if, right? I mean, if G has linear growth, then PC is equal to 1. Prove that it never occurs when it's not linear growth. And this took a few years. So this is, now we go to something I did. I did with co-authors, is to prove this, to answer this conjecture. And actually, we answer it by proving something stronger that I want to tell you a little bit about. So probabilists, you can wake up and start following again. So here is the theorem. So it's a theorem with Goswami, Raufi, Severo, and Yadin, and Franco Severo is in the room. And as I always say when I have a co-author in the room, if you have questions on this part of the talk, go ask him. He will probably answer it much better than I do. So anyway, here is the theorem. Take a graph, finite degree, okay? I don't want to assume that it's transitive, which if you think about it up to now was actually a key point. But let's ignore the fact that it's transitive. But let's assume something else. Let's assume something geometric about it. Let's assume that it satisfies an isoparametric inequality with dimension D, and let's assume D is larger than 4. The 4 is just for technical reasons. Actually, you would hope to get D larger than 1, but we are not there yet. So isoparametric inequality, meaning the size of any set, the boundary of the size of any boundary of a set is larger than constant times size of the set to the power 1 minus 1 over D. Okay? Standard isoparametric inequality in discrete setting. If this occurs, then I claim that there is a parameter p smaller than 1, such that for any finite set, the probability that its set is connected to infinity is larger than 1 minus exponential of minus 1/2 times the capacity of your graph. I don't want to define the capacity, but just think of it as a measure seen from infinity of your graph, of your set S. And there is one key property, and that's the only one that we need in this talk of this capacity, is that in this regime, the graph is actually transient, and just the capacity of 1 point is positive. But that tells you automatically that the probability that this point is connected to infinity is strictly larger than 0, which was exactly the definition of PC. Actually, notice that you could take, a priori, PC could depend on a point, because theta of P now, if you are not in something transitive, it could depend on, it's the probability that a certain point is connected to infinity. But the PC itself, even though theta of P is a function of X, the PC itself doesn't depend on X. So PC is well defined as a whole, but here, this thing is telling you that for this P, you are above PC, so it tells you that PC is smaller than 1. Okay? How does it relate to the question on Cayley graph? Because here we didn't assume the same thing as for a Cayley graph. Well, up to this recent result, what was known was the following. For instance, any group with polynomial growth by Gromov's theorem is virtually nilpotent, and this implies basically that any Cayley graph of this group, if it has superlinear growth, it contains a subgraph which is quasi-isomorphic to Z2. And this, then, because Z2 has PC smaller than 1, you can deduce that this graph has PC smaller than 1. It was known for a very long time. But notice that it does rely on a really non-trivial theorem. You need the classification of a group with polynomial growth. So the difficulty, ironically, came from big graph, which seems completely ridiculous because you definitely believe that the bigger the graph, the smaller the PC. But there is no clear monotonicity in graphs. So the second observation that has to be made to deduce our question from that is that, in fact, if the rate of growth of balls is sufficiently fast, then in the case of Cayley graph, you automatically get the isoparametric inequality. So it's something, so if the rate of growth is at least like the dimension D, then you get the isoparametric of dimension D. So that means that any superlinear growth Cayley graph actually satisfies the isoparametric inequality for every D. So in particular, for some D larger than 4. So when you combine both things, and this is really something which doesn't use percolation, it's really harmonic analysis and study of random walk in some sense. But the two things together give you the PC smaller than 1 for every Cayley graph. By the way, this idea of related isoparametric inequalities to percolation, this actually goes back to a question of Benjamini and Schramm to try to do that. So it didn't come from nowhere. There were some results, and one from Augusto, a beautiful result, which they did involve some stronger version of isoparametric inequality, so they didn't quite apply to answer a Benjamini-Schramm question, but they were already a big step towards. Okay, in the last 5 minutes, 7 minutes, I want to tell you a little bit how we get that, just like a glimpse at the proof. A glimpse, sorry. Okay, so the idea came, and I think this is the go-home message for probabilists. Percolation is one of the simplest probabilistic model, but there is one which is definitely simpler and very nice to study, which is random walk. Random walk you understand much better, and in particular the relation between the random walk behavior and isoparametric inequalities, like geometric properties of your graph. This goes back like way back. We understand very well random walk. So can we connect percolation to random walk? And that was really a question that we were trying to answer. I remember discussing that with Itai, Benjamini a lot, like how can we connect the two? And we found a way which to us was surprising at the beginning, but it's still surprising, but we are happy with it, so we don't complain too much. And the way is to use Gaussian free fit. So remember this Gaussian process that I defined, whatever the definition. The important thing about the Gaussian free field is that the covariance between 2 points is the green function of simple random walk. So the Gaussian free field is trivially related to random walk. But the point is that you can rewrite the Gaussian free field in such a way that this covariance between 2 points, this green function, can be written as an average with respect to this GFF of the probability that X is connected to Y, so really percolation probability, but not for Bernoulli percolation with parameter P at every edge, for Bernoulli percolation with a parameter at every edge that depends on the GFF. And it depends in the following way, that the probability that the edge is open is 1 minus exponential of minus the plus part of the Gaussian free field at one endpoint times the positive part of the Gaussian free field at the other point. This is a functional of your Gaussian free field. This is therefore a functional of your GFF. You average it. So you take an annealed probability of being connected. But this annealed, this additional randomness, it helps you a lot because it gives you an explicit almost expression, like something you really understand very well for probability of being connected. So of course, you could complain and say, well, yeah, okay, you can always add randomness and so on, but here, your edge density depends very much on the GFF, which itself has nothing to do with percolation. It's something which has a law which is not so simple to understand. In particular, sometimes the GFF is very large. And when it's very large, this probability is very close to 1. And when it's very small, this probability is very close to 0. So how could you relate? I mean, is it obvious that you can relate this to really probability of X connected to Y for some standard percolation with fixed parameter P? And what we did is that you can actually do it. So you can integrate out the randomness coming from the GFF. You decompose the GFF into Gaussian modes that have finite range, and you integrate out a little bit like people do in renormalization theory, in rigorous renormalization theory. You integrate out the randomness of the GFF, and you can actually prove that for some parameter P, very large, but fixed and deterministic, it doesn't depend on the GFF anymore. It's really just a parameter P. The probability that X is connected to Y is larger or equal to this annealed probability of connection. So overall, you prove that for this parameter, the probability of being connected, X connected to Y, is larger than the green function. And because the green function is understood and in particular does not decay too fast, you can deduce that P, this value of P, is actually larger or equal to PC. Therefore, PC is smaller than 1. So you first rewrite using additional randomness, you relate an annealed percolation in a random environment to the GFF, and then you integrate out the randomness using renormalization type ideas. I think it's a very nice strategy. I hope that it will have application, because if you think about it, proving existence of a phase transition in this type of models, you don't have so many tools. So you have this Peirce argument that I basically presented in the case of ZD. You have reflection positivity when the model is reflection positive for people who know about what that means, but it's very rare that it's reflection positive. Sometimes you can do renormalization directly, but these were basically the three only strategy. And this, I think, is fundamentally different from the other strategies. And it's probably going to have some application. At least I really hope so. Okay, just let me conclude by saying that here you see I'm using properties, I'm using the isoparametric inequality, so I'm using properties of the graph to deduce something about percolation. But there is no reason the thing would not go the other way, and actually sometimes it does. So there is a whole theory of studying percolation on Cayley graph to understand the geometry of the group behind it. And one beautiful example is this paper of Gaborio on lions, which answers really a question of measure group theory using percolation. So there is a very nice interplay between the two things. And to conclude on another easy conjecture, because I only gave you two very simple ones, so a third very simple one, which is a conjecture in this very same paper of Benjamini and Schramm, which says that a Cayley graph is non-amenable, meaning that it has isoparametric dimension infinity, so just the size of the boundary of groups, of sets, is always larger than constant times the size of the set. There is no 1 minus 1 over d, it's just size of the set. It's non-amenable if and only if PC is smaller than PU, strictly. You know what PC is now. What is PU? Well, PU is the probability that there exists a unique infinite connected component. Because if you think about it, there may be cases where you would have infinitely many infinite connected components. So there is a smallest value above which you start to have a unique one, and you are non-amenable if and only if PC is smaller than PU. The simplest case of non-amenable graph that you can imagine is a tree. And in the case of the tree, PC is very simple to compute. It's 1 over d if it's a d plus 1 array tree. And on the other hand, PU in this case is also simple to compute. It's 1. So this is one example of an answer. Obviously, that's not the difficult part of the conjecture. So here, this is an open conjecture. There are some partial results proving that for any non-amenable group, there exists a Cayley graph satisfying that. But the question is it true for any Cayley graph? And this is a beautiful question, which you won't believe me, but I'm having 9 seconds left. So thank you.
So are there questions?
We are allowed to have questions. Very good.
On your proof slide, you were saying G does not decay very fast, so that you can conclude.
Yeah.
So this means that you have some you know generally that you have exponential decay, even if your graph is not...
Okay, so there are, I mean, it's a very good question. So the first thing is, if you are on a transitive graph, then you know from the theorem that I presented that probability of being connected to distance n decays exponentially fast. In fact, you can also prove that the expected size of the cluster, the sum of the probability of 0 connected to x, is finite. But the sum of the green function for a fixed point is infinite. So this, for instance, is a sufficient information. When you are transitive, if you are not transitive, in fact, you cannot really do that. You have to do something a little bit better. So you tilt your GFF, you increase your GFF a little bit, and you look basically at GFF plus 1. And there you actually get here a bound. I mean, to really get this bound, you need to do something a little bit cleverer. But to just give the idea, it was simpler to go through that. But indeed, otherwise you would have problems because the green function can decay exponentially fast on certain graphs. There is no problem with that.
So on this slide, do you have any estimate on the P? How it relates to the C and the D? Or?
So, I guess this we could keep track of it. The interesting thing would be to be able to prove that when D is larger, I mean, when the degree of the graph, it's rather the connection to the degree of the graph, which is interesting. We would like to say that when the degree is larger, you get better and better PC, like smaller and smaller. And this, I don't think we have good estimates on that.
But in terms of the dimension and the constant? In the
yeah, I mean, probably you can keep track of them, but it's going to be nightmarish. In the renormalization scheme, when you integrate out the randomness, there, you do crazy things. I mean, I like short proofs, so we really went from the geodesic one, and there, like, you don't want to keep track of. It will humiliate me completely if you start. We are going to get something terrible. Didn't try to optimize.
So, since there are no more questions, let's thank Hugo again.